it's a great pleasure to introduce Marco Pistoia, who's heading a division at JP Morgan in charge of quantitative analysis and quantum computing and related topics. He did pioneering work in several areas of computing, quantum information, and different areas where there were many patents and many publications and books. So he has been influential both at IBM and at JP Morgan, and it's a great honor and pleasure to have him here. And please go ahead, Marco.
Thank you, Franco. Thank you for inviting me to be here today. And it's a great honor for me to present this conference. And I hope maybe another time I will be able to join in person. That would be great, because I have actually never been to Africa, and it would be a fantastic trip, I believe. But so I wanted to quickly share my screen and give you an overview of doing indeed of quantum computing and quantum communication at JP Morgan Chase. Full screen mode. Okay. So first of all, I wanted to say that at JP Morgan Chase, we created a research group called Global Technology Applied Research. And we are conducting research on both the quantum computing and quantum communications. So I will explain what these two technologies are. For sure, everybody's familiar with quantum computing and this conference. However, I think it's interesting to see that there is more than just quantum computing when it comes to quantum technology. And the first question that everybody asks me all the time is like, why is a bank doing research in quantum? And I wanted to show you this diagram at the bottom of the slide, which comes from a study made by McKinsey and Company, a game plan for quantum computing. This study shows a very interesting fact. And it shows that among all the industry domains that will be benefiting from quantum computing, finance is the first one. Finance is actually expected to benefit quantum computing not only in the short and in the not only in the long term, but also in the medium term, and also in the short term. So why is that? Why is that the case that finance will benefit from quantum computing before other domains like the pharmaceutical domain, the energy domain, the advanced industries domain, and so on? The reason is that in finance, we have a lot of use cases, many more in finance than in other industry sectors. For example, portfolio optimization, risk analysis, option pricing, machine learning, particularly natural language processing, and fraud detection, and so on. The thing about these use cases is that they all have exponential complexity, so they lend themselves to quantum computing. But there is also another factor to take into account when it comes to finance. Time is of the essence. So when it comes to finance, we need to have answers right away. We need to have immediate answers. We cannot wait for forever to get an answer, because the financial market is very volatile. Things change quickly. For this reason, we need to have an answer immediately, and the answer has to be accurate as well. That's why we believe, according to this McKinsey & Company study, we agree that finance will be like really revolutionized by quantum computing. And for this reason, we are actually investing in this domain and building a team at JP Morgan Chase to do research in quantum computing. However, quantum computing poses two risks, and I want you to discuss these with you today. So here are the two risks. The first one is the fact that quantum computing is not yet ready to be used in production. So the risk here is that companies might decide to wait until quantum computing becomes fully usable in production. And if that happens, I think when that happens, when quantum computing will be powerful enough to support use cases, particularly financial use cases, at that point, it will become particularly problematic for a company to catch up on quantum computing. And so for this reason, it's important to become quantum ready now. So what are the solutions to this risk, to the risk of being surpassed by competitors? The first solution is to be proactive and build and own a portfolio of quantum algorithms and applications, to build the hardware agnostic solutions, to monitor the quantum hardware ecosystem, and to protect the IP of the company, the intellectual property of the company. So why do we need to build a portfolio of quantum algorithms and applications if these algorithms and applications are not yet usable? And the reason is that we cannot just wait and wait for these solutions to become usable, because if we do that, it takes a while to actually build solutions. And so if we're waiting, if we try to wait, we will be caught off guard. We will be not prepared for quantum advantage. And why do we need to build hardware agnostic solutions? So when we build our algorithms at JP Morgan Chase, we have actually noticed that when you write a quantum algorithm, you have to actually make the algorithm interface a particular quantum computer. And if you decide to change the quantum computer, you will have to change your algorithm. This sometimes the code, sometimes even some of the characteristics of the algorithm. So it becomes really detrimental to have solutions that are hardware specific, because we don't know who is going to be the winning platform for quantum computing. We don't know who is going to be the winner in this battle of the quantum hardware providers. So for this reason, keeping a neutral approach that allows us to be hardware agnostic is actually the right approach in our opinion, because it allows us to start thinking about the time in which quantum computing becomes an engineering solution. Also, it's important to be hardware agnostic because our research is accelerated by this level of independence from the hardware. So how did we achieve this? We achieved it by integrating in our quantum computing stack a circuit compiler that generates circuits that are specific to particular hardware providers. So we don't have to hard code these features in our code, but the compiler generates circuits that are specific for that hardware. At the same time, we monitor the quantum hardware ecosystem to make sure that we understand different technologies of quantum computing. For example, superconducting qubits, ion traps, neutral atoms, and so on. So I wanted to show you an algorithm that, so we actually published.
Marco, quick question. The font is very small, because is it possible to, because it's taking a small, because I'm getting emails here that the slides are a bit too small to see. So
this one here too?
That one I think is easy, but the next two ones, they seem to be like smaller font, because it seems to be that the part of the screen is all black. So I'm wondering if it can be made larger perhaps or not. If it is easy, if it is difficult, then forget it.
Let me see, 1 second. Probably there's something I can do. View, zoom. Sure, we can do, I think maybe this one. No. View, zoom. I thought maybe something like this. I can actually.
Exactly, like this would be larger. Okay.
Yes. So I'm sorry for that. Thank you for bringing me to this to my attention. But maybe maybe there's even more that I can do, like 150%, something like that. Is that a little better?
Or perhaps if you click the top right button, you can get more of the screen. The top right square.
Yes, absolutely.
Exactly there.
Thank you. And maybe yeah, I think this is good. Very good. Sorry, another thing I wanted to confess is that I'm using a Windows computer. I'm not really a Windows person. I use a Mac all the time, so I'm a little like slow in even the button that you mentioned. That was. By the way, I also see chats. So okay. So this was not meant for me. Okay. So if you have a question, and you don't have to wait for me finishing the presentation. Everybody, please feel free to interrupt me. But I wanted to mention one of the use cases that we addressed in our work is called option pricing. It's like a financial use case. We published a paper in 2020 in the Quantum Journal, and the algorithm for option pricing is called amplitude estimation. It's an algorithm with a quadratic speedup, which means that the complexity of the solution is still exponential. However, the exponent is half of the exponent that we had at the beginning. In other words, it's almost like you take the initial complexity and you actually compute the square roots. So it's that's why it's called the quadratic speedup. Now, it's interesting. It's a good algorithm because quadratic speedup is also very good. I mean, not everything can achieve exponential speedup in quantum computing. However, there is a problem. We actually realized after writing that paper that generating the inputs necessary to execute the amplitude estimation algorithm may also have exponential complexity. So it's good to have an algorithm that reduces the complexity with quadratic speedup, but then the application layer that generates the distribution for the algorithm has exponential complexity, and then it negates the quantum advantage of the algorithm. So as you can see here, it says often the bottleneck in these quantum algorithms. So what we actually devised is an algorithm that actually has polynomial complexity. So it actually achieves exponential speedup. And the interesting novelty about this algorithm is that, which was also published in the Quantum Journal, the interesting advantage of this algorithm, the novelty, is that it uses mid-circuit measurement and qubit reuse. Mid-circuit measurement and reuse is also known with its acronym MCMR. It's a technology that is available in the Quantinuum quantum computer. It used to be Honeywell. And Quantinuum offers MCMR and also quantum conditional logic. So what is MCMR? As you can see at the beginning in quantum computing, traditional quantum computers require that you measure all the qubits at once at the end of the execution of the circuits. With mid-circuit measurement and reuse, you can actually measure qubits in isolation during the execution of the program, and then you can actually reset those qubits. So effectively, you now have more qubits. Think about it, like in this example, you have 5 qubits. With MCMR, we only need the 3 qubits, so we save the 2 qubits. So I can actually use those 2 qubits to solve the problems of larger size. So in other words, the MCMR allows you to reuse qubits, and so effectively you have more qubits available for your algorithm. So I just wanted to tell you that it's very interesting that in a bank we have been able to publish our work. So I wanted to show you. Our group is called Applied Research. So www.jpmorgan.com/technology/applied research. You can see here our publications and patents from the year 2020 on, because in 2020 it's when we actually finally created this research lab at JP Morgan Chase. So we have a lot of papers because we believe that publications are very important in order for us to receive feedback from the scientific community, and also in order for us to let other people know about our work so that we can actually collaborate with other researchers worldwide. So we have papers here, including this one that has been published in Nature just a couple of months ago. And we have a bunch of archive preprints as well, and so on. So if you go to our website, you will be able to see our work and all of our algorithms as well. Moving right along, I wanted to talk to you about the second risk of quantum computing. So risk number 2 is that quantum computing can actually break today's public key cryptographic algorithms. The reason is the following. Today's public key cryptographic algorithms, such as RSA, Diffie-Hellman, and the elliptic curve encryption algorithm, are based on very difficult problems that cannot be solved efficiently on a classical computer. For example, RSA, the security of RSA relies on the difficulty of factoring very large numbers into prime factors. This problem has exponential complexity. However, while it is very difficult to factor a very large number into prime factors using a classical computer, it's not difficult to do that on a quantum computer of the future. In fact, a quantum computer can do that very efficiently, and not now, but in the future. It has been estimated that a quantum computer with only 13,500 qubits can break cryptography and allow a private key to be computed. So I can compute somebody's private key starting from that person's public key in only 6 months using 13,500 qubits. And also this algorithm, it's like a Shor's algorithm. The way they actually proved that you can do this in 6 months using only 13,500 qubits is by using mid-circle measurement and reuse as well, just out of curiosity. So what are the solutions to this problem? One is to do post-quantum cryptography, and the other one is quantum key distribution. So let me explain post-quantum cryptography and quantum key distribution for a moment. So post-quantum cryptography consists of classical cryptographic algorithms, just like RSA, Diffie-Hellman, and the elliptic curve cryptographic algorithms. However, post-quantum cryptography algorithms have not yet been broken by quantum computers. The fact that they have not yet been broken by quantum computers doesn't mean that they will never be broken by quantum computers. So post-quantum cryptography is a good solution. It provides digital signatures, key exchange protocols, and so on. However, the security of post-quantum cryptography is still based on the inability of algorithms to break cryptographic solutions. We don't know if these algorithms that are being selected right now are going to resist attacks. So at the same time, we are performing research from a different point of view, the point of view of quantum key distribution. Quantum key distribution is actually a technology that belongs to another domain of quantum, which is called quantum communications. In quantum key distribution, two parties can compute the same key, the same symmetric cryptographic key, by exchanging a quantum state with each other. The quantum states of the two parties are initially entangled, and then the two parties can measure the quantum states and achieve the same key. Once the two parties have achieved the same key, they can continue to use the key securely. And the advantage of quantum key distribution, as opposed to post-quantum cryptography, is that quantum key distribution has been mathematically proven to be unbreakable. So who proved this theorem, that quantum key distribution is mathematically unbreakable? Ironically, it's the same professor, Professor Peter Shor, who proved that RSA Diffie-Hellman and the elliptic curve algorithms can be broken with his algorithm called the Shor's algorithm. So it's almost like it makes us feel that quantum key distribution, it adds a little bit of an interesting aspect to it, because the same person who proved that traditional cryptography is vulnerable is also the one who proved that quantum key distribution is unbreakable. It's very ironic and interesting. But let me actually show you what we have done in this space. So in February of this year, we you can see here that we published an article that was also picked up by news and reporters, and we were JP Morgan Chase alongside Toshiba and Siena built the first quantum key distribution network for metropolitan areas. So it's a quantum key distribution network in which the security is achieved by exchanging quantum keys in metropolitan areas, because the distance so far cannot go beyond 100 kilometers. However, the two advantages of this solution is that we proved that we can actually encrypt 800 gigabits per second, 800 gigabits of data per second. And on the same fiber, we were able to multiplex the key exchange, the encrypted data, and a lot of other data for a total of 2.4 terabits per second. So what I'm trying to say here is that this solution is actually real. It's not like a toy experiment. As a matter of fact, we secured a mission-critical blockchain application on top of this QKD network. And the application was the one used by JP Morgan Chase for payments. So it was an interesting proof of concept. I also wanted to mention that quantum key distribution is already used in production in numerous countries. For example, Singapore, South Korea, Switzerland, England, and also other countries in the European Union. So it is something that is becoming more and more significant, because the combination of post-quantum cryptography and quantum key distribution appears to be the most secure solution to the threats of quantum computing. So if you want to read more about this, we published a paper with all the researchers from JP Morgan Chase, Toshiba, and Siena, and the paper is available on archive right now. I wanted to tell you how quantum key distribution works, a quick overview. So let's call the two parties Alice and Bob, which is standard terminology in cryptography, right? You know, we always call the two parties Alice and Bob. So in quantum key distribution, you have to have two channels. On one channel, the red one, it's called the quantum channel. You use that channel for transferring the key, the symmetric key that Alice and Bob will share to perform encryption. And then there is the green channel. It's called the authenticated and public classical channel. On this channel, the data, encrypted data, is transferred. So the first step is for Alice and Bob to agree on the same cryptographic key. The cryptographic key is obtained with Alice and Bob sharing the same key as quantum states, as a quantum state. The key is a quantum state that Alice and Bob share with each other. They're entangled with each other. And then Alice and Bob can independently measure the key, the quantum state, and achieve the same identical key. Once the key has been computed and exchanged, another advantage of quantum key distribution is that no attacker can actually compute the key. And this is because there are two principles of quantum mechanics. One is called the principle of no cloning, and the other one, the principle of measurement, that pretty much guarantee that an attacker, let's call the attacker Eve will not be able to copy the key or measure the key without Alice and Bob detecting the presence of the attacker. As soon as Alice and Bob detect the presence of the attacker, they will be able to stop the communication without any loss of information. So once the key has been established, Alice and Bob can continue their communication on the green channel, the authenticated and public classical channel. So more details about the experiment that we conducted in our lab at JP Morgan Chase. There are 5 experiments here. Let's start the first 4. The first 4 are like tests that we did to verify that the solution was actually robust. Number 5 is the eavesdropper detection, our ability to detect the presence of Eve in case Eve tries to copy or measure the key. And then the 6th experiment was the blockchain application, which, as I said, we deployed on top of our quantum key distribution network. So I think I want to make the case at this point that quantum key distribution and quantum computing are 2 incredibly promising directions of technology for the future. And quantum computing has the potential of solving very complex problems accurately and in a very timely fashion. And quantum key distribution has the mathematical guarantee that the key exchanged by the 2 parties in the communication will not be shareable, will not be stolen by attackers. So it's great to do research in these 2 fields. Personally, I feel excited that I had the opportunity to do this research with my team. So I just wanted to conclude by giving you these 4 points. So for people who want to, who are interested in quantum computing, this is exactly the right time. Quantum computing is not yet usable in production, but it will be usable in production, perhaps sooner than we expect. So it's important to start your quantum readiness journey now. Once you have started your journey, you have to identify first wave applications. The first wave applications are those applications that are actually the low-hanging fruits, those applications that benefit from quantum computing in the short term. Since we have many applications to look at, it makes sense to start with those that will benefit from quantum computing in the short term. And then I wanted to emphasize that quantum technology has a very sophisticated stack, which is actually very diverse. At the top, we have the user interface, user experience. Then underneath, the application layer, the algorithmic layer, and then the circuit layer, and then the hardware. So depending on what your company or your academic institution is performing research on, or what is the business that your company is after, you have to identify your place in the quantum stack and start building assets in this at this layer. And then, of course, it's time to build a team of experts. It's interesting that quantum computing is a very diverse technology. So you can be a mathematician, a physicist, a computer scientist, an engineer, and there are jobs for everyone, even people that are working at the user interface level. So it's a very interesting journey at this point, and I think it's very exciting. So this is the end of my talk, and I will be happy to take questions.
Let me see. Can you hear me now? Many
Yes,
thanks for the great talk. And indeed, many people talk about these applications of quantum computing to materials, to chemicals, pharmaceuticals, but at least in the physics community, there is far less talk about the application to finance. I didn't know it was much larger, actually. When I saw the first plot, I say, wow, this is, and indeed, there are many NP-complete problems, combinatorial optimization. So it makes sense. And so this is eye-opening data, and it's very important. So let me look at the, if you have questions, please feel free to type it into the chat. Some of the applications people do in the quantum, as you know very well, is to generate random numbers. If you could get good quality random numbers, then you can calculate integrals. You calculate integrals, you can do Monte Carlo, and you can do, I guess, this Black-Scholes equation, or you can do some option price. You can do many things involving good quality. So is this an important application for finance to have good quality quantum numbers, or this is like a marginal improvement?
No, Franco, you actually raised a very important point. It is a very important application to generate, to have the ability to generate pure random numbers, because we know that classically there is no such a thing as a random number. Classically, everything is pseudo-random. So there are attacks that can take place when the numbers are generated classically. If an attacker has been able to identify the pattern behind the generation of the random numbers, that becomes a problem. But with quantum computing, we have the guarantee that the numbers are really random. And so we are actually investigating how this can benefit us in finance. A very simple application is to do two-factor authentication, in which you have a random number, you have to enter it into into a portal, and the fact that the number is purely random guarantees that the system is secure. But we also looked at the tokenization of credit card numbers using pure quantum random numbers. So thank you for asking this question, Franco, because it's actually something that I didn't mention during my presentation.
When I was doing Monte Carlo as a graduate student, I was worrying about the period of my pseudo-random number generator. So what I did is I was changing the seed. So therefore, I had one random number generator and then picking up the seeds somewhat at random from the first sequence and feeding it as seeds for some other sequences. So I'm sure people in the banking, finance have done it. If you do tricks like this, you could essentially get pretty good random numbers, because the seeds are picked from somewhat at random from the first generation, and then you feed them into some other sequences. You know what I'm saying is like, if you mix different pseudo-random numbers in some non-trivial ways, you might be able to get them sufficiently random. And I assume people must have looked into this in the past. And
absolutely, this is a great point. Yes, the
it might be a much cheaper way to do it. If the quantum computer is not working, then you can do the pseudo-random. But then, like, I remember this discussion that was many years ago, how to use different seeds to feed them every once in a while to the, because we're trying to improve our quantum Monte Carlo. Was many years ago. Also, are you also using, like, for Black-Scholes equation, kind of like quantum computing, or?
Not really yet, but I wouldn't exclude that in the future we might do it, because we're also in our own journey, so we're also learning new things every day. So
because the Black-Scholes equation can be mapped to the diffusion equation, which is essentially the diffusion equation is Schrödinger equation in imaginary time. So some of the techniques applied to see the Schrödinger equation time evolution or the diffusion equation have been shifted to the Black-Scholes equation or some other related equations. And then Omololu, do you have a question there?
Yes, I have a question. Actually, I wanted to respond to your question. If you use the random number generator to generate a seed and do something like you're saying, the set of random numbers you get, you won't know the distribution they belong to, right?
Sorry, I didn't understand the question. Can you repeat if you don't mind?
It depends how you pick up the seeds. It depends how you do it.
Okay. Yeah, so Marco, the question I have is related to the first one that Franco asked. So money is finite, right? So if you use a quantum computer, you're not going to get exponentially more money than you had before. So how would it benefit, like, if you use a quantum computer and I don't?
So I think for quantum random numbers, I see an advantage in additional security, because it's the true randomness of these numbers makes the system difficult to attack. So that's what, but I think Frank also leveraged another use in like Monte Carlo simulations by creating true random seeds. However, I think so far I have seen more of a demand in the area of security. And by the way, an interesting thing I wanted to say, yes, quantum computers are not yet usable in production, as I said before. So we cannot use quantum computers to solve our daily portfolio optimization problems or option pricing problems. But when it comes to quantum random number generations, the quantum computers that we have today are already usable. So that's one of the few things that is already working with quantum computers.
Well, this is good. This is good.
Thank you.
Thank you.
Any other questions?
I have many, but I'll try to get the speaker some other day to ask him any questions, because it's a very interesting topic with many interesting aspects. So it's but I don't want to monopolize this question and answer session.
Sorry, Marco, do you have like a software that is open source that you can let people use?
Yes. So, so when I was at IBM, so I spent 24 years as a researcher at the IBM Watson Research Lab in New York. And I was actually leading an effort for quantum computing algorithms and applications. And we created an open source project called the QA6-Second. So we're actually using it here at JP Morgan Chase. And it's really something that is very good because it's open source. So it's I like working on open source projects because we get benefits from the entire community. I think quantum computing is still at a stage in which we should not compete with each other. Instead, we should collaborate with each other. Because that's one of the reasons why I'm excited to be here today, because I want to see the opportunity of new collaborations with Franco, with you guys. It's a stage in which collaboration is crucial.
Okay.
Indeed, today we had a talk by Nathan Shamath talking about open software, a unitary fund, and it's about the essentially open software. It's very important. So you were one of the people who pioneered QSkit.
Yes, I was actually managing some open source repository for QSkits, the ones that related to algorithms and applications. And then I left IBM and moved to JP Morgan Chase, but I still use it because of the advantage of having an open source project.
I see. This is a very, very important software. Here in our group, we did like Qtip some time ago to also make it available to people. And one of the developers, Paul Nation, is in Yorktown Heights. He's in
Yes,
IBM.
I know him. Yes.
He was a postdoc in our group.
Oh, wow. That's amazing. I just got a message on Zoom from Honorine. The message is, please, Marco, how could we contact you later? And I would like to invite you guys to write me an email if you have any questions. My email is marco.pistoia@jpmorgan.com. I would like to type it here, but I still haven't found out how to do it. I'm so sorry. I actually, since I clicked on the button that says I will enter it live, now it doesn't let me type. I know I can type it.
It's okay. It can be found people on Google. There's no problem.
Yes, but I was able to find how to type it. So please, I'm excited about the collaboration with you guys. If you want to contact me. Also, I wanted to say we are hiring at JP Morgan Chase in the area of quantum computing and quantum communication. So if you are passionate about these two topics, it's a good time to to apply.
Okay.
Great.
Thank you very much, Marco.
Thank you. So it was a real pleasure to be here today, and I am honored that I was invited. So thank you, Franco, for inviting me. And
has been a great talk, and it has been eye-opening, especially the first slide when you said that there were more applications in finance than materials. Say, wow, because most people are talking about materials and pharmaceuticals, but finance is much bigger.
I know it was a surprise to me as well. And at JP Morgan Chase, we are our research group. We are constantly interacting with the technologists. For example, the quantitative research, the quantitative researchers, everybody who is doing portfolio optimization, risk analysis, option pricing, because by doing that, we get use cases, and we are actually learning a lot about what we can do with quantum computing.
Okay.
It's very exciting. Great, great.
Thank you very much, Marco. Marco, please, could you send us your slides so that we will share it with everybody?
Absolutely. I would send them to Franco.
Okay.
That'd be great. Thank you very much. It's been a great pleasure and an eye-opening presentation, and I'm sure that people will be thinking about this for a while. This is great, great. Thanks.
Yes.
Thank you. I appreciate it. Bye, everyone. Thank you.
Okay, bye, Marco. Thank you. Yep.
Bye.